Good morning, I'm Robert, and I'm a research fellow working on making new materials for optoelectronic applications. So that includes photovoltaics. And the reason we're so interested in solar energy is because the amount of energy we get from terrestrial sunlight is 3 orders of magnitude larger than the world's electricity demand. But despite that, photovoltaics only contribute to 1.7% of energy supply. So one way to increase scaling is to increase the efficiency of these solar cells without significantly increasing the manufacturing cost. And one way of doing that is to make a tandem solar cell. So this is where we put together 2 semiconductors with 2 different band gaps. If we only have one band gap, then photons with energy below the band gap do not get absorbed, and photons with energy above the band gap lose their excess energy as heat. So this places a limit on the maximum achievable efficiency. For example, for silicon solar cells, after 4 decades of research, those have reached 26% efficiency, and that's very close to their limit. If we put 2 band gaps together then we can convert a larger fraction of the solar spectrum into electrical energy. And one pair of materials that works well is a metal halo perovskite and the silicon cell. The silicon cell absorbs near-infrared light, and the perovskite absorbs the visible light. And after only 5 years of research, this has already reached a certified efficiency of 27.3%. And with the perovskites, we can also tune the band gap through the composition, which means that we can also make a tandem between 2 different perovskites, which can achieve the same efficiency as the perovskite silicon tandem, but with much lower manufacturing cost. So a key piece of equipment from the Royce Institute that allows us to push this emerging area of research is the Ambient cluster tool, and in particular the Perovskite Evaporator, which allows us to co-evaporate from inorganic and organic sources to grow perovskite thin films. And here you can see an image of a thin film that we already grew during commissioning. And this allows us to develop new tunnel junctions to couple together the subcells so that the tandem efficiency is larger than the efficiency of each subcell. It also allows us to grow perovskite conformally onto texture substrates and get the maximum possible efficiencies. And we can also more rigorously explore different compositions to get the optimal band gaps and optimal electronic properties. So thank you.